Hello everyone, I'm Jason Jia from AMD Xilinx. I'm very glad to have this opportunity to give the presentation on our XVDPU, a high-performance CNN accelerator on the Versal platform powered by the AI engine. I will divide my presentation into 7 parts. First of all, I'm going to start with introduction and the top-level design. Then I will discuss the design of AI engine at each loop level. Next, I'm going to introduce the data flow optimizations, then the design of ALU engine at the PL side, and then the evaluations. Machine learning using CNN has been greatly developed in recent years. Most of the CNN models require more computing units and memory bandwidth. Researchers spend most of their time on CPU and GPU. However, CPU and GPU are difficult to meet the requirements of latency and power consumption for the applications, especially for embedded scenarios. The ASIC's long development period makes it hard to keep pace with the latest innovation. Compared with CPU and GPU, FPGA has the advantages of low latency and low power consumption, and the programmability makes FPGA be more flexible than the ASIC. Engineers have developed a large number of CNN network accelerators on FPGAs. Xilinx presents a new class of reconfigurable devices called the ACAP to provide a solution for the computation and the computation needs of modern applications. We propose a CNN accelerator based on ACAP. Here we introduce the top-level block design. Our design is based on ACAP device XCVC1902. The proposed design is a configurable deep learning accelerator and makes full use of PL, PS, and AIE array. Our accelerator is optimized for popular CNN models like VGG, ResNet, YOLO, SSD, MobileNet, and others. The AI engine cores are the key roles to process the convolution calculations. The other operations are mapped on the PL side for the on-chip scheduling and maze calculations. The feature map data for each batches and the weight data shared among batches are buffered on chip via the data mover. The other non-com operations are aggregated into a general engine called ALU. The host control runs the Xilinx Lattice AI in the PS side to manage the runtime. There are 400 AIE cores in VC1902, 8 rows by 50 columns. Our design goal is to make accelerator as scalable as possible to be adaptive to different CNN models. The scalability has 3 levels: core level, basic graph level, and the batch level. At the core level, we use AIE to do the convolution and some of the nonlinear functions. Each AIE core computes a subvolume of the output feature map in one iteration. The size of the subvolume is controlled by parameters at runtime in order to achieve optimal efficiency. These parameters are calculated offline according to sets of layers in the network model. An array of AIE cores forms the AIE graph. At the graph level, we have 3 configurations called C16, C32, and C16-4. Each configuration could be implemented with multiple batch, for example C16B1, C32B3, C64B5. For the core level design, the figure above shows the basic MAC operation in one AIE core, which does 2 by 8 by 8 matrix multiplication in one cycle. We map the input feature map as 2 rows by 8 input channels, map weight data as 8 input channels and 8 output channels. Therefore, the result output feature map is mapped as 2 rows by 8 output channels. The figure below shows the profiling of AIE base pipeline. In one iteration of AIE computation, the base pipeline is looped over multiple dimensions, including kernel window, input channel, and output weights. After loop on input channel dimension, partial result of output feature map of this iteration is produced. For the graph level design, by placing multiple AIE cores in different dimensions, we can get the AIE graph. We have three scalable graphs, C16, C32, and C64. The dimension factors and graph level granularity of the three graphs are listed in Table 1 and Table 2. Take the topology of C16 as example. Each width stream broadcasts to 4 cores vertically to get 8 output row parallelism. Each IFM stream broadcasts to 2 cores horizontally to get 16 output channel parallelism. In order to accumulate a long input channel, the casted stream between the two horizontal neighbor cores are utilized. C62 and C64 graphs have more AA cores on OC dimension based on C16 graph, so that the AFM stream will broadcast to more columns. For the batch level design, each graph could be implemented with multiple batches according to the chip resources and performance requirement. Multiple input images can be processed synchronously. The width data could be shared among multiple batches, so that only one batch of width data is buffered. The figure shows the design of C16 batch 2 graph. Compared with the batch 1 graph, the number of input width streams are not increased, while each width stream broadcasts to more cores. On the PL side, the data mover for buffering width data from DDR to PL is also shared among multiple batches. The shared width design shaves bandwidth requirement of DDR AIE shim and also the on-chip RAM resources. Typically, data flow of feature map between layers have to interact through DDR I/O. Reading and writing of DDR are flexible through Xe4 interfaces, but the large latency of DDR I/O will lead to performance loss. Therefore, we adopt feature map stationary strategy, aka FMS, to keep feature map stay at on-chip RAM during its life cycle. In this way, not only bandwidth pressure of DDR I/O is reduced, but also data acquisition time is shortened. Certainly, not all styles of feature maps can achieve FMS. The most basic requirement is there is enough RAM space left for the remaining layers to store the intermediate results. The rich ultra-RAM resources on Versal chip make it achievable. This figure illustrates an example of FMS on Reset 50. Except for loading AFM in the first layer and saving OFM in the last layer, there are no more DDR I/O access for the feature map. Then only the weight data of each layer should be loaded into the on-chip RAM from DDR. In some large layers, the DDR I/O for weight data is the main bottleneck. To optimize this point, the long load width design is adopted. The width data arrangement in the DDR is shuffled. As shown in the figure, the output channel dimension is divided into 4 groups, and the input channel dimension in each output group is interleaved. Then the data width of each port could be increased to 512 bits. Thus, one long load instruction could transmit for 4 by n output channels into 4 banks with continuously DDR access. The DDR I/O efficiency is then improved a lot. Generally, a series of non-com operations will not be triggered at the same time due to the interlayer data dependency, so we design a hardware accelerator called ALU on PL side to perform non-com operations with shared resources. Operations supported by ALU include die-by-com, mass pooling, average pooling, activation functions like ReLU, leak ReLU, PReLU, and ReLU6, etc. Then batch normalization and item-wise addition and multiplication. The ALU engine supports wide parameter range, such as kernel size ranging from 1 by 1 to 256 by 256 for pooling and DirectConf operations. Thus, many popular CN models can be deployed on our hardware accelerator. In our design, the calculation paradigm of ALU engine is 128. The combined design of AAE for COM and ALU for non-COM can better balance the resource utilization, new feature support, and efficiency of the whole system. As the evaluation section, here the left table summarizes the configurable parameters of the proposed scalable system and the selected values in this evaluation. The resource utilization is shown in the right table. We select the Xilinx B4096 3-core design implemented on the Xilinx ZCU102 as comparison. It can be seen that AAE replaces a large number of DSP slices and provides much higher compute power. The proposed system supports a wide range of int8 precision CN models, like classification, segmentation, phase detection, etc. The table lists the performance of some typical networks in YTCA library model rule, which includes more than 100 popular CN models. Our C62B3 design achieves 8.8 times peak performance compared with B4096 3-core design. From the frames per second of end-to-end, the performance of our design is significantly improved compared to the ZCU102 design. Taking the Resident 50 model as an example, one enables the FMS strategy. Our proposed system with C32B3 achieves 9.81 times end-to-end performance improvement than that on ZCU102, which is higher than the theoretically 8.8 times peak performance improvement, indicating better efficiency. When the batch size increases, the FMS strategy keeps the model cycles be stable. Furthermore, we have explored the C32B8 configuration. Its performance reaches up to 4050 FPS, which achieves 24 times performance acceleration compared with ZCU102. This chart illustrates the relationship of the performance vs execute cycles on our multi-batch design, ranging from batch 1 to batch 6. As mentioned before, when the batch size increases, the FMS strategy keeps the model cycles be stable, such as Resident 50. For many models like YOLO V3 that couldn't achieve FMS, will have to run with more cycles at larger batch sizes, which is limited by the DDR/I/O bandwidth. Then their performance drop along limitation curve shown as a dashed line. Besides, there are some models that didn't reach the limitation curve, like MobileNet, so that CPU processing pre- and post-processing is a bottleneck. To summarize the proposed design, XVDPU is a heterogeneous computing system including AI engine, PR fabric, and PS CPU, which leverages the advantages of 7nm Versal 8-cap platform. Several optimizations like multi-batch, share weights, feature map stationary, and long load weights are adopted to improve I/O efficiency and reduce on-chip resource utilization. ALU engine maps kinds of non-COM operations with compact resource utilization. More than 100 popular CN networks are supported. The C32B3 provides 8.8 times peak performance compared to 16nm Z09 MP-SoC design. The C32B8 implementation achieved 4050 FPS for the Resident 50 model. Thank you all very much for listening.